Today we are going to talk about how all motion is relative except light and what that means. Welcome to Easy Science. Today we're diving into one of the most mind-bending ideas in physics, the relativity of motion, and why light breaks the rules. From fast-moving trains to time-slowing clocks, let's explore how our understanding of motion completely changed with Einstein's theory of relativity. All motion is relative. In classical physics, Newtonian mechanics, motion is always measured relative to a reference point. There's no universal rest or absolute motion. You can only describe motion by comparing it to something else. Examples: a train moves at 80 kilometers per hour relative to the ground. A person walking inside the train at 5 kilometers per hour in the same direction is moving at 85 kilometers per hour. Relative to the ground, but only 5 kilometers per hour. Relative to the train, there is no fixed point in the universe that serves as an absolute reference. Everything moves relative to something else. The speed of light is absolute. Although all motion is relative, the speed of light is not. According to Einstein's special relativity, the speed of light in a vacuum is always the same: 299,792,458 meter per second, or approximately 3 times 10 meters per second. This holds true regardless of how fast the source or the observer is moving. Example: if a flashlight shines a beam forward on a moving train, both someone on the train and someone outside will measure the speed of the light as 310 meters per second. This defies the classical idea that speed should simply add or subtract and leads to surprising consequences. Consequences of constant light speed. To preserve the constant speed of light for all observers, the universe has to adjust how space and time behave. First consequences: time dilation. Time slows down for objects in motion from the viewpoint of someone standing still. Explanation: imagine a light clock, a beam bouncing between mirrors. When moving, the light travels a longer diagonal path. Since light speed doesn't change, the clock ticks slower. Formula: T equals T square root 1 V squared per C squared, where T equals time from stationary observer's view. T equals proper time moving clock. V equals velocity of the object. C equals speed of light. Result: fast-moving clocks tick slower. Second consequences: length contraction. Objects appear shorter in the direction of motion, as seen by a stationary observer. Explanation: space compresses along the direction of motion to keep the speed of light consistent. Formula: L equals L times square root 1 V squared per C squared, where L equals observed length. L equals proper length at rest. Result: moving objects shrink in length along their direction of motion. Conclusion: to sum up, all motion is relative. There's no absolute rest. The speed of light is absolute, no matter who observes it. To uphold this, nature bends the rules. Time dilation slows down clocks in motion. Length contraction shortens moving objects. These strange effects aren't just theory, they've been proven with atomic clocks on airplanes and particles in accelerators. Thanks for watching. If you found this video helpful, don't forget to like, share, and subscribe to Easy Science for more clear and fun explanations. Got questions or suggestions? Drop them in the comments. We love hearing from you.